All right, let's talk about something really interesting today. It's a Python framework called NecroStack, and its whole mission is, well, pretty ambitious: to bring some serious order to the wild, natural chaos of modern software systems.
You know the feeling, right? If you've ever worked on an asynchronous, event-driven system, you've been there. A message just vanishes. Data gets mangled somewhere down the line. Or, my personal favorite, you're trying to debug a chain reaction of events that seems to have a mind of its own. It feels like you're constantly fighting against entropy. So, why is this so common?
So here's our game plan. We're going to start by really digging into the problem, what we're calling software's natural entropy. Then we'll look at NecroStack's super unique, biologically inspired solution. We'll break down its core anatomy, see how it's designed to handle the real world of production, and finally get to the big one. What's the actual payoff for you as a developer?
Okay, let's get into the problem itself. And the big idea here is that these systems don't just fail because of bugs or mistakes. Nope, a lot of the time, failure is just the natural state of things when you're dealing with all this asynchronous complexity.
The source material calls these the four horsemen of system entropy. And honestly, it's the perfect name. So, first up, implicit schemas. This is when the service sending data and the one receiving it slowly get out of sync until things break. Then you've got state mutation. This is a sneaky one where some process accidentally messes with data that another process was counting on. Classic who moved my cheese problem. Of course, there's the dreaded infinite loop, where events just ping-pong back and forth forever, burning up all your resources. And last but not least, observability black holes. That terrifying feeling when you have no idea how a request got from point A to point Z.
So, how in the world do you fight back against all that chaos? Well, NecroStack's approach is really cool because it doesn't look to other software for answers. It looks to biology.
And this right here is the absolute core of it. Instead of relying on tribal knowledge or hoping developers just remember the right way to pass a message, that's an implicit convention, NecroStack forces the rules on you. It builds explicit constraints right into the architecture. It's a lot like how biology uses things like cell walls and DNA to build incredibly complex organisms from a very strict set of rules.
So how does it pull this off? Well, the entire framework is built on three really simple but really powerful ideas. These are the fundamental building blocks of everything you'll do in NecroStack: events, organs, and the spine.
First up, the event. Now, this is not just some random dictionary of data. It's a strictly defined, validated and, this is the magic word, frozen. Frozen means it's immutable. Once it's created, you literally cannot change it. And that single decision is huge. It instantly kills two of our four horsemen: schema drift and state mutation. The data is what it is forever. Next, we have the organ. This is where your actual code, your business logic lives. You can think of it like a specialized cell in a body. It does one thing, and it does it really well. It listens for a very specific type of event, does its work, and then maybe, just maybe, it creates new events. The key is that organs are designed to be stateless. They don't have memory. This makes them incredibly predictable and, you guessed it, super easy to test.
And finally, holding it all together is the spine. The spine is basically the central nervous system. Its one and only job is to grab an event and deliver it to the right organ that's listening for it. It doesn't hold data, it has no business logic, it's just a pure, stateless delivery service. Which means the flow of your whole system becomes deterministic and way easier to understand.
So let's put it all together. What does a message's journey actually look like? Step 1, an immutable event gets created and it's validated right away. Step 2, the spine picks up this new event from your message queue. Step 3, the spine, like a perfect mail carrier, delivers that event to the exact organ that's subscribed to that event type. And finally, step 4, the organ does its job and, if necessary, creates brand new events to keep the process going. It's simple, predictable, and incredibly clean.
Okay, so the theory sounds solid, but how does this stand up in the messy, chaotic, real world of a production environment? Let's take a look.
One of the smartest things here is the flexibility with backends. When you're just coding on your laptop or running tests, you can use a super fast, simple in-memory backend. But when you're ready to go live, you swap it out for something robust like Redis streams. And the best part? You don't have to change a single line of your actual application logic. You get persistence, scalability, and that absolutely critical guarantee of at least once delivery.
And this is where you can tell it's truly built for production. It doesn't just hope things go well, it assumes they will fail. You've got built-in retries with exponential backoff for those little network blips. You've got dead letter queues to safely park messages that just won't process. There are even circuit breakers to protect struggling services, and automatic recovery if a consumer crashes halfway through its work. This thing is battle-ready.
So, when you add it all up, the immutable events, the stateless organs, the production safeguards, it's all pointing towards one big idea. What is the ultimate payoff for putting up with these constraints? Well, it all comes down to a shift towards correctness first. I mean, just look at this quote. This isn't just a goal or a feature. It's a formally verified invariant. Now, that's a fancy way of saying that the core logic of the framework isn't just tested. Its correctness is mathematically proven. That means it's guaranteed to behave predictably, even in the weirdest edge cases you could never dream up on your own.
And here is a perfect, concrete example of what that means in practice. Remember that infinite loop, Horseman? The one that can bring your entire system down? NecroStack just eliminates it. It sets a hard limit on how many steps an event chain can have. If it hits 10,000, for example, the system just safely stops. An entire category of catastrophic bugs is just gone, designed right out of existence.
And that's really the heart of it. Using a framework like this is more than just a different way to write code. It's a philosophical change. You're engineering a system where entire classes of common, painful, asynchronous bugs are literally impossible to create in the first place.
And that really brings us to the final big question. NecroStack makes a deliberate trade-off. It gives up a little bit of that do-anything-you-want flexibility in exchange for massive gains in correctness and predictability. It makes the argument that for a lot of critical systems, that is absolutely the right trade to make. So as you think about your own projects, is it time to prioritize that correctness, maybe even over absolute flexibility? It's a powerful question and definitely one worth thinking about.